Hello, we're finally here in the last chapter of Calculus 3, and we have to start off the chapter by looking at vector fields. We will use those vector fields to allow us to calculate some line integrals over vector fields later, but first we want to talk about the vector fields themselves. So a vector field is a function, and we've seen vector functions before in chapter 13. And so this won't be brand new. Some of the notation will be a little bit new. Some of the ways we look at things will be a little bit new, but the vector functions themselves are not. So a vector field is a function whose domain is a set of points from either 2D real numbers or 3D real numbers. And then the range, the output of the function, is going to be in these vector worlds. So these are vector fields, V2 or V3. And they are kind of similar to like the notation of R2 or R3 that represent the reals in 2 dimension or the reals in 3 dimensions. V2 is a 2-dimensional vector. It's a 2x1 vector, 2 rows, 1 column. And V3 is a 3-dimensional vector. It's 3 rows, 1 column. You may see them written in column form. So you might see something like 1, 2, or you might see something like 1, 2 in that way. It depends on the class you're taking, and then it also depends on just, this could be for convenience, but technically when they're written in these different ways, this one is a column vector, and then the other one is actually a row vector. I just want you to be aware that sometimes in this class we will represent a column vector in a row. And I don't want to call it incorrect, but it is kind of sloppy notation to do so. Okay, moving on. So what we're going to do is, like, let's say our domain is a subset of the reals in 2 dimensions. Then our vector field on the 2-dimensional reals is a vector function, and it assigns this vector at big F of xy to each point xy that we get from the 2-dimensional reals. And so what I mean by that is this notation right here. So F of xy, and it's F hat to indicate that it's a vector, has components. In the I component, we have a P of xy, so that's a scalar function. And then in the J component, we have another scalar function, and that's Q of xy. So these are scalar functions, but they are in the components of a vector. So altogether, it is a vector function. Similarly, we could see this in 3D. If our domain is 3-dimensional, then and we have a vector field that's 3-dimensional, then the components will be P, Q, and R, where each of P, Q, and R is a function of X, Y, and Z. All right, so some places where we might see vector fields, just so we get a feel for like, what the heck is a vector field and what does it look like? We might see weather maps that show wind velocity at various points in space, or you might see a map that shows ocean currents. There's airflow, that's also a vector field, magnetic fields, and gravitational fields. There are many others, but these are just a few. So here are a couple of pictures. You can see where we've got these flow lines that are showing up in this picture right here. All those flow lines are part of the vector field. For different xy values, you plug them in and you get a different vector and you plot it. And then you pick another xy value, you plug it into your vector, and then you plot it. Similarly, this one right here, this one looks like a river flow or a water flow. So river, water flow. And notice there's a rock in the middle of the river. And so the water has to flow around it, which creates a change in the flow of the water, which also represents a change in the flow of the vector field. Now, without an application, but just a vector function, we can just graph our own vector fields. So here I have a 2D vector field, and here I have a 3D vector field. I'll let you guess which one is harder to draw. Basically, we're going to draw one in 3D and then hopefully never again. because it's really hard. So in this next page, I want to look at if little f is a scalar function of two or more variables, then the gradient of f is a vector field either on R2 or R3, depending on whether our scalar function f was a function of two variables or three variables. That will dictate to us whether the gradient vector has two components or three components. We calculated the gradient vector field before in chapter 14, and now we're going to use it. The gradient vector field is special because the vectors of the gradient vector field will be perpendicular to the level curves of the scalar function. Okay, so for example, I could tell you that in the above picture here on the 2D one, the level curves are actually circles. My circles are bad, the arrows are good. But what this is showing is that the vector field, each of those little vectors is perpendicular to the actual level curve that comes from the scalar function. Okay, so first let's look at sketching of some vector fields. So for this one, we're given a vector function, big F of xy is equal to the vector xy. So we need to graph a few, not a lot, just a few different little vectors. So let's see how we do that. We're going to need an x column, a y column, and then a vector column. So the first column will be x, the second column will be y, and the third column will be f equals the vector that we have. Okay, so the easiest thing to draw here is if x is 0 and y is 0, then my vector function is a vector with components 0, 0. So if I was to try to draw this, the x and the y tell me start at 0, 0. The vector says move to the right or left by 0 and then up or down by 0. So basically I get nothing. I get a point. That's it. Nothing more. Let's try something else. If x was 0 and y was 1, then what that tells me is I have a vector 0, 1. So here's what that looks like. I would go to the point 0, 1. So the x value is 0, the y value is 1. Here's my point. Now the vector says starting at that point, move 0 units in the x direction. Well, that means don't move, right? And then it says move 1 direction positive in the y direction. So that's just going to make me go up by 1 unit, and then I'll draw a little arrow at the end. So these vectors are not position vectors. They are vectors that start at the given point that we assign them. Let's try 1, 1. So 1, 1, I'm going to go to the point 1, 1. Let's get our vector as well. It'll be the vector 1, 1. So I go to the point 1, 1. I draw a point. And then I go to my vector, and it says move to the right by 1 and up by 1. So I do that, and I connect those dots, and I put an arrow and at the last point. Okay. I could also do something like, let's see, -1, -1. So I'd go to -1, -1, draw a point. Then the vector says go to the left by 1 and down by 1, and then connect and put an arrow on the end. And there's one of my vectors. I'll do one more because I only really have one more color I can draw with. Let's do 2, 1. So when x is 2 and y is 1, I get the vector 2, 1. So I'm going to go to the point 2, 1, draw my point, and then the vector says move to the right by 2 for x and up by 1 for y. Draw another point, connect those dots, and put an arrow at the end. And that is the vector 2, 1. Okay, so definitely not position vectors. The hard part is to transition from how we thought about vectors before, where we drew all of them so that they started at the origin and then pointed out from there. These start at the xy value that we are using from R2 or R3, and then they go in the direction that the vector tells them to. Okay, here's another one. This is big F of xy is equal to, and this should actually be, sorry about this, this should be big F of xyz because I have a three-dimensional vector, xy, 1. So what's going on here is I need an x column, I need a y column, I need a z column, and I need a big F equals the x, y, 1 vector. Okay, I also need to put in an xyz octant, and I've used that special graphing paper to give me something a little bit easier to graph with. So I'm drawing my octant on the graph paper. And now I should put some tick marks for the x values, y values, and z values. Okay, now I'm going to start with the vector 1, 1, 1. Okay, I'm picking x to be 1, y to be 1, and z it has to be 1. Because f is equal to x, y, 1. So my vector now is 1, 1, 1. Okay, I'm going to go out by 1 for x, over by 1 for y, and up by 1 for z. So that's out, over, and up. It kind of looks like my point is on the origin, even though it's actually not. All right, then that's the start of my vector. Now it says to go in the direction 1, 1, 1. Well, what's basically going to happen is we aren't going to be able to see what's going on here because I go over by 1, and what we can't see is where that really is. And then I go 1 in the y direction, and I go up again, and it looks like this is a terrible point to draw to try to graph. I really can't graph this. So yeah, that was bad. Hard to see. Let's see if there's something better we could do. How about 3? X is 3, y is 4, z has to be 1. Okay, so we have the vector 3, 4, 1. Let's see if this gives us something better. So I go out by 3 for x, over by 4 for y, up by 1 for z, and I draw my point. Perfect. Now, what my vector tells me to do is go out by 3 for x, over by 4 for y, and up by 1 for z. Draw another point and connect those two and draw an arrow. There's my vector. I could do one more for giggles. Let's try 0, 0, 1. That would give me 0, 0, 1 for a vector. So I would start at no movement for x and y, just go up by 1 for z. Okay, and then the vector says don't move at all for x and y, just go up by 1 for z and draw an arrow. All right, I'm done. I don't want to draw any more vectors on here. In WebAssign, you'll have a better tool for doing this, but my thoughts on graphing three-dimensional vectors is you do it once and you hopefully never do it again because it is a bit painful. All right, let's see what we've got here. I'm going to see if I can get this. Let me see. I need to get CalcPlot 3D to show up here. Let's see if I can do this. And to hide that, create a link. Or how about I just copy that, Control C. I'm going to bring this over here. Paste. Enter. Oh, goodness gracious. Okay, C3D Libre. Oops. Okay, we have CalcPlot 3D, and I actually wanted, let's see. Okay, So what this is asking us to do, let me go back to my screen here. Use software to graph the following vector fields. And we're going to choose a vector field. We've got instructions here. We need to choose the vector field option. We're going to restrict our view to 2D, and then we're going to scale the vectors to adjust the length. Okay. So I'm going to go into CalcPlot 3D. And I'm going to take off the one that's on there by unselecting it. I want to add a vector field to my graph, and so I want to select it as well. My f of xy was x squared, and then my y, so this is kind of weird. We use m, n, and p in CalcPlot 3D. M is the x component, n is the y component, which for us is y squared. And oh, we can already start to see it drawing on there. I am not going to have a z component. I'm going to leave it as 0. And I can kind of see what's going on here. It does say we can restrict our view to 2D. Down here we've got a box, so I'm going to do that. Oh, that's much better. So there's this area right here. We've got an option for a rectangular array, a spherical array. That's interesting. Cylindrical array, that's weird. We'll stick with rectangular since we're working with x's and y's. The number of vectors that we want to see, well, along the x-axis, it looks like they had a default of 9. We could make that, 20 if we wanted. And we see a whole lot more. Along the y-axis, we could do 20 as well. Holy cow. Along the z-axis, let's play with this a little bit. What happens because we don't have a z? What if you're like, oh, well, I don't want any along the z-axis, so I'm going to make that 0. Your whole graph goes away because along the z-axis, that's on the xy plane. So we need at least the xy plane to show. Okay, now notice the different lengths of each of those vectors, right? As we get closer to the origin, they're smaller, and as we move away from the origin, they're bigger. Let's go ahead and scale the vectors to adjust the length. What we're going to do actually is scale. It says scale vectors by dividing by 4. Let's go ahead and scale by dividing by like 8. See what happens. That's a little bit easier to look at, right? And we could even, scale more than that. We'll go by 10, and it's even easier to look at. So I can take a snip of this and put this in our work. We're going to do control paste. There it is. Huge. Let's go ahead and shrink that down a lot. And we have it here now. Okay. This would have been really, really hard for me to draw if I had tried to do it by hand, right? That's a whole lot of vectors to put on there. And so I don't want to do it. So that's why we're having use software to graph the following vector fields so we can see what they look like. Let's try another one. Well, actually, before I even go to trying another one, let's talk a little bit about this one. Notice that from the negative x direction and the negative y direction, the vectors are pointing towards the origin. It's like the flow is going towards the origin. But then as we move to the right and up, all the vectors are flowing away. So they're all kind of pointing in the same direction, depending. Like if we could see like a line along y equals x, something like that. You can see a whole lot of vectors that are parallel to that line. We could see maybe like right here, not quite a straight line, right? The flow of the vectors is changing there. Same down here. The flow of the vectors has more of a hyperbolic shape, actually. Okay, so it's just things to notice. That's about it. All right, let's look at CalcPlot 3D again. We have another function where the x component is y and the y component is sine of x. And then we can have that show up here. It's already scaled by 10. I'm going to go back to the default of 4 just to see how that looks. Here we can kind of see a bit of like the sinusoidal with respect to y. Like notice along the y-axis, we've got a sort of going down and then up. That's like a sinusoidal sort of shape going on there. Let's get a snip of this one and put it in our paper. Oops. So a new one. And then we'll go to our work. And holy cow, that's huge. Shrink that down a whole lot. And then put it in here. Okay. And so now I can draw all over it. So we're seeing this sort of shape here and down here. Oops. This one's going from the right to the left, and on top it's going from the left to the right. And then we're seeing on the right and the left going through the x-axis that same sort of shape, right? So that's kind of our flow line. And if we go a little bit higher up, we see like it goes up and then comes down and then goes down and then comes up. So the closer we get to the origin, the more peaked those hills are. All right, let's see a three-dimensional one. Let's see how CalcPlot 3D does with X, Y, Z for components. So go in here. Now I've got X, Y, and Z. And I have it restricted to 2D right now, and that's great, but I kind of want to see it in 3D. So I'm going to take off that restriction to 2D. And along the z-axis, instead of having just 1, I'm going to put in 5. Holy cow. I'm going to change how many are along the x-axis to 10 and the y-axis to 10 as well. All right. So you see the 5 levels of z? Got 1 on top and then down another 3 is at the xy plane, and then 2 more levels below that. That's the number of vectors along the z-axis. And then of course along the x and y axes I chose 10 and 10. Pretty crazy look to it. Right? Really hard to see what's going on. Let's try to get this back into an upright position. Z is pointing up. And I'm going to spin this a little bit. Whew, it's hard. All right. I hope you get the point there, though. I'm going to scroll into it so we can kind of see it a little bit better. All right, let's go ahead and get a snip of this. Really, it's crazy looking. But notice that all of the vectors are pointing outward. Let's go ahead and get that picture down here. All the vectors are just pointing away from the origin, from any starting position. That's what we're seeing. And as we get further and further away from the origin, the vectors are actually longer and longer as well. So that's, just making observations. That's really it. And just to show you how you can do this too. Okay. So I think WebAssign is going to have, multiple choice selections. But before you even look at those, I'd recommend that you just go ahead and go to CalcPlot 3D and just graph these. Like, don't try to narrow down the options in WebAssign. Just graph it and then compare what you get with the choices and choose the one that looks like yours. All right, number 3. For the following function, we're going to sketch a few level curves as well as the gradient fields along these curves. And we want to remember that the relationship between the level curves of a surface and the gradient vector of a function should be a perpendicular relationship. Okay, so first things first, we have to know that this right here is the scalar function. Okay, we want the gradient vector function. And that's going to be where we take that del operator of the scalar function. And we have to remember that it is composed of the first partials of each. So the first partial with respect to x, the first partial with respect to y. So the first partial with respect to x is just 2x, with respect to y is just 2y. Okay. The scalar function itself, well, let's look at level curves. And so for level curves, our function is x squared plus y squared, which is a positive number. So that can only ever be equal to some constant k greater than or equal to 0. So remember with a level curve, we take our function, x squared plus y squared, and we set it equal to k. And then we can, I can just state here for k equals 1, 4, 9, etc. We get a bunch of circles. So the level curves are circles. And then we have to remember that all vectors from the gradient vector field are perpendicular to the level curves. Okay, so I want to look and see if we can go into CalcPlot 3D and do this. So I'm going to remove the P component, and I'm going to put in 2x and 2y because those were the components of our gradient vector. Along the z-axis, we want just one. Okay, we want to restrict the view to 2D. All right, that's great. I want to scale the vectors by, let's go with 8, make them a little bit smaller. And then what I want to put on here, I want to add something to the graph. I want to add, let's see, how do I want to put it? Yeah, we'll just do z equals, oh, hey, they already have it. Z equals x squared plus y squared. But I want to see it as contours. So I got a contour plot. I click this just so you see it. There's this little icon, and it looks like it's got red lines in it. I've got my mouse hovering over it. It's just below the number of grid lines is 30. To the right of that, click on that little graph. Oops. And it will give you contour plot settings. So I'm going to do a first level value of, well, we could do 0, and we can do step sizes from there. We can choose the number of contours that we want, the number of grid points. We have all these things that we can do, and then we can do create plot. And so what it did, because I chose the number of contours to be 11, I have 11 circles here, and they're all in such a position that the gradient vectors are perpendicular to them, and we can fairly easily see that. So this looks like a perfectly good place to go ahead and get a snip of this and put it in our paper. So we're going to paste this. We get a huge one. And then we can put this on here. So this is why I was writing everything kind of to the side so that we would have the space here to just put this graph in. We could do this by hand. I don't want to. And honestly, it's not the circles that are a problem. It's all those little vectors that I'd have to draw. Now I want you to notice something. The vectors that are closer to the origin are shorter. The vectors that are further away from the origin are longer. And so it's like as we get further and further out on the level curves, that actually coincides with z becoming bigger and bigger and bigger. After all, f of xy equals x squared plus y squared is a paraboloid. So this is a paraboloid opening up, and we're just seeing it projected onto the xy plane. And each of the bigger and bigger circles is a level of z that is higher and higher, okay? And the gradient vectors are bigger and bigger the higher up we get on z. Just an observation. That's all that it is, okay? All right, a vector field F is called a conservative vector field. This is a big definition. You need to know this, okay? F is called a conservative vector field if it is the gradient vector field of some scalar function f. Okay, so what we're saying here is when we come across a vector, like just random old vector, like for example, let's just go back up here, just this y sine of x. We don't know if this vector is just any old vector or if it's special. Like, is it a gradient vector? Are y and sine of x the first partials of some scalar function? That's what we want to know if we want to determine if a vector field is a conservative vector field. So another way to say that too is if our vector field equals the gradient of f, then the vector field is conservative, okay? So those two things I just highlighted are saying the exact same thing. Hopefully one of them makes more sense to you than the other. But in this situation, if we have a vector field that is a gradient vector field, then we can call little f, the scalar function little f is the potential function of the vector field. And we're going to use this later in the chapter. We're going to be starting with a gradient vector field, and we're going to work backwards with integration in order to figure out what scalar function did this vector field come from. So some examples of some scalar functions we might work with: volume, mass, speed, time. Some examples of vector functions: velocity, force, and whatnot, and so on and so forth. So that kind of concludes the vector field portion. You're really just getting comfortable with a vector field. I would say it's more important that you're practicing using technology in order to graph vector fields, but definitely try a few by hand so that you're good just graphing, like, I don't know, 3 or 4 vectors. Next time we will pick up with 16.2 and we'll learn about line integrals. But in the meantime, if you have any questions at all, please reach out.